Hello everyone, welcome to today's session on magnetic effects of electric current. So in this, we will look at the force on current carrying conductors in a magnetic field. So far what we have learned in earlier sessions, like what are the effects, the magnetic effects that current carrying conductor can produce, and also the direction of the magnetic field, how the magnetic field is produced and what's the direction of the magnetic field. And also if that magnetic field cuts the real magnetic field of when we keep a magnet within that. For example, we looked at the applications of electric motor or a generator, right? So in that, you have a magnet and you have a magnetic field produced by the current that exerts some force. So now we will, in this session, we'll learn more about what that force is and what is its direction and how that will be helpful. Okay. All right. So the magnetic field, that's the force on a conductor. Let's look at this setup now, right? So I have a stand here and I have, this is basically a circuit. Okay. This is like, I have a, uh, I have a rod AB, which is kind of hanging to a wire, the current carrying wire, and it's tied at two ends, A and B. And the setup is such a way that if the switch is on, the current I flows from here, from B to A. In this direction, the current will flow from B to A. So when the current is flowing from B to A, as per the as per our earlier learning, that the magnetic field is produced surrounding that rod, right? Surrounding that rod AB. So here, the magnetic field is produced like this. You agree? So this is how the magnetic field is produced across that current carrying rod. Now, if that is now placed between a horseshoe magnet, okay, it's a horseshoe magnet whose north pole is here and the south pole is here, that means the magnetic field lines are upward direction. You understood? So we have a magnetic field going up and we have a current flowing in this direction. Then as these both fields cut, there exists some force. No? How that force impacts this rod is what we need to study. So for this, before we get into like how, in which direction that force is exerted, we need to learn about a rule called Fleming's left hand rule. Okay. So earlier we used the right hand thumb rule, right, to find the direction of the magnetic field. Now here, when we have three fields, one is current, one is the magnetic field, then there exists a force that creates a motion, right? So there are three parameters here. So how the direction can be found if we know two directions, right? That is about Fleming's left hand rule. So what Fleming's left hand rule says is the three fingers, right? The thumb, the forefinger and the middle finger, you need to put it in this way. That means it is like perpendicular to each other. So if you look at these two are perpendicular and then these two are also perpendicular. So if you can hold your left hand, the three fingers in this way, then the field means the magnetic field direction. The forefinger indicates the magnetic field direction and the middle finger indicates the direction of the current. So if that is the current, then the thumb indicates the direction of force. Okay. So in our earlier case, let's move back, right? Then in here, so I have electric current, which is the middle finger. The direction is towards me, right? From B to A. That means the current is going in this direction. When the current is going in this direction, right? So and then the magnetic field is upwards, right? So that means I need to keep like this, right? This is the direction. The middle finger is towards me. That's the direction of the current. And the magnetic field is towards up. It's going upward. Then what is the thumb? Thumb is in which direction? This is to the left. That means the rod will be pushed towards left. You understood? Or on the paper, if you want to know, the rod will be pushed towards this direction. On the paper, it is right. Okay, so it will be pushed towards, sorry, it is still left. Yeah, it is pushed towards left. Okay, so that's how, using the Fleming's left hand rule, you can find the direction of the force. When you have a magnetic field, the current, the magnetic field produced by the current, and the magnetic field that you have introduced using a magnet, when you have two, the magnetic field and the current, then you can find the direction of the magnetic direction of the force using left hand, Fleming's left hand rule. Okay, now here, what happens? So here the rod will be pushed towards left. Now, if I reverse the current, right? Reverse the current means what I need to do? I need to swap the battery terminals. That means this time, yeah, the current will go this side. I'm drawing an imaginary line. Okay. And that if the current is flowing in this direction, then the current will flow from A to B, right? A to B. That means the direction of the current has changed now. So the magnetic field is still upward, right? So, sorry, the forefinger shows the magnetic field. So that is still upward. And the current is in these directions, away from me, A to B. Then what is the direction of the force? That is towards right. That means this time the rod will be, sorry, the rod will be pushed towards right. Okay, so what is happening is, in this case, a force, let's say F amount of force is exerted on the rod that will push either to the right or to the left. So what are our observations here? The number one, right? When I is flowing, right? When current I is flowing from B to A, right? When the current I is flowing from B to A, comma, magnetic field, comma, magnetic field is upwards, then force is which direction? Towards left, towards left. Similarly, when we reverse it, right? When I is from B to A, right? When the electric current is from not B to A, right? So in this scenario, it is from A to B. When we reverse the battery terminals, it is from A to B. So when the current is in A to B and the magnetic field, right? And the magnetic field is, we haven't changed. So magnetic field is upwards, then what is happening? The force is towards right. So basically, what is happening here? The direction of the force depends on number three, right? So basically here, direction of force depends on which parameters? Number one, that is magnetic field direction, right? Number two, current direction. Right? These are the two parameters. One is the direction of the current decides which way the force is exerted. Similarly, the magnetic field direction. So we did by reversing the current. What happens if we reverse the magnet itself, right? So now it is from north to south. If I replace the magnet such a way that, right, if I replace the magnet upside down, so here it is north and here it is south, then the magnetic field lines will be downwards. So then what happens? The same scenario, if the magnetic field which is forefinger, right? If that is upwards earlier case. Now, earlier case was this. The magnetic field is upwards and the current is towards me and the force is to the left. Now, the same scenario, if it becomes like this, right? The same scenario, if it becomes like this, that means the magnetic field is downwards and the current is towards me, and then the direction of the force is towards right. So it exactly getting reversed, opposite. So it depends on both the factors, the direction of the current and also the direction of the magnetic field. How for the force, the direction of the force depends on both the factors, the field, the direction of magnetic field and the direction of current. Okay. And also, if you need more force, what you need to do? You need to the intensity of force, right? Or the magnitude of force depends on the amount of current that you are passing. So if you pass more current, then more deflection can be produced. And similarly, if you can increase the strength of the magnetic field, right? The horseshoe magnet, if you add two horseshoe magnets, it gives more intensity of magnetic field. So more force will be applied. Okay. So the fourth observation, what we can say is the magnitude of force. What is this, guys? The magnitude means the quantity. The magnitude of force depends on number one, the amount of current, right? The amount of current, the amount of current, and number two, the strength of magnetic field. You agree, right? The strength of magnetic field. So in this experiment, we came to know a force is exerted and how to find the direction of that force and how much magnitude of force it is. So the magnitude of force depends on two factors, that is the amount of current flowing through the circuit as well as the strength of the magnetic field. So that's about the force on a conductor. And we also learned what is Fleming's left-hand rule. So Fleming's left-hand rule, we already learned, right? So basically what is happening here when uh, when current, right? When current I is flowing through a conductor, when current I is flowing through the conductor, comma, conductor in a magnetic field, in a magnetic field, comma, there exerts a force F whose direction whose direction can be found using left hand rule. So where thumb indicates the direction of force. The thumb indicates the direction of force, and the forefinger indicates the direction of what, guys? Magnetic field. Direction of magnetic field. And the middle finger indicates the direction of current. The middle finger indicates the direction of current. So that is what the Fleming's left-hand rule, and all these three fingers should be perpendicular to each other. Okay, now let's look at this example and use Fleming's left-hand rule to find the direction of the magnetic force. Right. So an electron enters a magnetic field at right angle to it. So here is the electron. So the electron is entering the magnetic field, which is horizontal. An electron, see, here is, let's say, these three fingers is the magnetic field, and an electron is entering perpendicular into the magnetic field downwards, right? The direction of force acting on the electron will be. So how the direction of force will be. So when electron is moving from up to down, then automatically what is the direction of current should be opposite. That's what we know, right? The direction of current is opposite to the direction of the flow of the electrons, right? So when electron is moving downwards, that means the current flow should be upward. So now I got the direction of I, and the magnetic field is in this direction. So magnetic field is forefinger, and what is okay? All right. So let's see this. Right? So this is the direction of the magnetic field, and this indicates the direction of the current, which is upwards. Then the thumb indicates the direction of the force. So the direction of the force is into the paper, or it is into, right? Into the plane, or towards. So what is that? Okay. To the right of the paper? No. To the left? No. Out of the page? No. Into the page, right? So it is into the page, guys, because this is the magnetic field and this is electric current and this is the force which is towards into the paper, right? So that's how we can do that. So that is into the paper. So what we have used, we just need to remember the forefinger is the magnetic field and the middle finger is the current and thumb is the direction of motion, which is force. So if we just align our fingers into the example given, then we can easily find the direction of force. All right, so that's about force and a current carrying conductor and also Fleming's left hand rule. Now, what are the applications of magnetic field? Right? So the major applications of magnetic field, we learned that is a motor, right? Wherever, so electric motor is one thing, generator is one thing, right? Uh, yeah, generator I can give, yeah, motor, generator, and many other electrical appliances where a force should be exerted. Now, in a medical field, there is a key application of this magnetic field and the current magnetic field produced by the current carrying conductor, that is MRI. So whenever we go to hospitals for some or the other issues, so the GP generally suggests for an MRI for a body organ. So what is this MRI? MRI is basically magnetic resonance imaging. Okay, so basically what it does is the magnetic field. It just draws the shape of the magnetic field surrounding that object, right? That organ. So it indicates like how the shape of the organ, right? For example, heart, right, or liver, right? So when there is a setup, that MRI machine, which has both the current, it passes an electric current, which produces a magnetic field, and which will be placed within the magnetic field. Then that magnetic lines cut across the organs, and wherever there is an objection, that they will not be able to penetrate. So wherever the magnetic field has stopped, so that direction you can get onto the image. So that image is magnetic resonance image, that is MRI, that will give you the size and shape of our body organs. Based on the size and shape of the organs, the doctors can examine whether there is any problem with the size of the organ or any projections or any deficiencies, right? Any defects in that. For example, brain. MRI scan is majorly for most of the body organs and the brain as well. So this MRI scan is used to find the shape of the brain and also any brain tumors. Okay, so that's the application of magnetic field. Okay, in medical field, it is used heavily. There are many devices. One major application of magnetic field, the effects of magnetic field is MRI scans. Okay, all right, guys. Then let's also look at the domestic electric circuit, right? So in our household, we already learned in electricity that all the household connections are in which series are parallel. Guys, if you recall, it is parallel. Household connections are connected in parallel. Household circuits are connected in parallel. Why they are connected in parallel? I gave you many the reasons, right? Because the effective resistance in parallel reduces drastically. That's one thing, right? The resistance. That means in the household circuit there will be less resistance. That means the flow of current is easy and uh, you will not lose much of the current, right? Now, let's see how the household circuit is, right? So this is what we will have is we will have a fuse, and then we will have an electricity meter, and then we will have a distribution switch within our home, like how the current needs to go to different circuits. Okay, like so here we need to know what wires we will have, right? So from the transformer or from the power supply, we will get a live wire, which is red in color. So live wire is red. So the live wire is always red in color. And then there is another wire called neutral. So neutral will not carry any current. Live wire only carries the current. Okay. Now the live wire is what? Black in color. And then there is also when we need three-phase current. So this is two-phase. In general, our households require two-phase current where you have live wire and neutral wire. And there are some appliances, if you see, which will have a bigger, if you look at our socket, 3-pin socket, right? So there, the top part is a little thicker. So what is that thicker part is that is connected to a earth wire that is green in color. So we will see what's the use of that and why we need earthing. Okay. Now, so two-phase current is basically live and neutral wire. So, and the potential difference between live and neutral wire is how much, guys, for household? Neutral wire is 220 volts. So the potential difference between these two lines, the live wire and the neutral wire is 220 volts. That's what you see here, right? So this is red wire and this is black wire, and the potential difference is 220 volts. And we learned about fuse, right? In earlier in electricity, we learned what is fuse. Fuse is kind of a protective system that can help the circuits when there is a surge of electricity or more power is drawn from the circuit or more power enter the circuit, right? Overload or high surge of current enter into the circuit, then there in the fuse there is a thin wire with low melting point that heats up, melts and breaks the circuit so that the remaining circuit is saved, is protected, right? So that's the function of a fuse. And then electric meter just to capture like how much current is being consumed in the household. Based on that, we will get the electricity bill. And then the distribution switches. Let's say I have 10 rooms in my home, right? So you cannot pause uh, a single switch to send current to all the 10 rooms, right? So there will be distribution. Okay, east side, let's handle with this switch. West side, this switch, like that, right? So there will be some distribution mechanism that they follow. Now, this green wire, what is this? Earth wire. Earth wire, why the earth wire is connected? In case a more amount of current is flown into the device, then that excess amount of current is absorbed into the earth wire, and that earth wire is grouted into the earth. That's why it is called earth wire. So if you observe in our flats or at our household, there will be a steel wire, a steel thin plate or some setup that is digged, that is buried into the earth. And from that, a wire is drawn, and that wire is connected into our circuit. So any surplus current is absorbed into the earth. That's the use of earthing wire. So it is mostly useful for uh, high voltage, high rated appliances like AC, right? For a AC, you need to have a three socket, right? And for geyser, right? So for such appliances, you need more uh, high rated, more current, or more current you need. And in case of any sudden increase, see, we already have fuse that protects the system. In case the current is sufficient to the circuit, but you have, for example, all the appliances are switched off, only AC is on. So in case some excess amount of current comes into the AC supply, then what it happens is the earth wire absorbs that and put it back into the earth. It is kind of a device level control, appliance level control. Okay. So yeah, that's the setup in the household, and our household circuit is connected in parallel, and the energy consumed is noted in the meter in terms of kilowatt hours, right? So each kilowatt hour we can calculate using how many watts. You know that, right? We learned about the energy consumed. So what is the energy consumed? Power is VI. So energy consumed is nothing but our work done. That is W into Q, right? So if we need to write in terms of I, then Q equal to IT. That means voltage into I into the amount of time it is consumed. So that is W. That you will get into seconds. If you multiply with if you multiply with the 3600, then you will get into hours. And if you multiply with into 10 power 3, then you get that into kilowatt hours. Multiply or divide, you need to see, right? So it's a W. This is the amount of energy consumed that is measured in kilowatt hours. So per kilowatt hour, there will be a charge. If it is 200 units of current is consumed, 200 into based on the rate, you will get the electricity bill. So this is how the household circuits are connected. Okay. So this is just for educational purposes. Okay. All right, guys. So in today's session, what we learned? So we learned about the force on a conductor and how to find that direction of the force using Fleming's left-hand rule. So in Fleming's left-hand rule, we have three fingers in the perpendicular direction. One, the forefinger indicates the magnetic field, and the thumb indicates the direction of force, and the middle finger indicates the direction of current. Okay. And we also looked at one example how to get into that. And also we learned about the applications of magnetic field the in medical field, right? So MRI is the key example that is used, right? And then what is a domestic electric circuit? So in domestic electric circuit, we learned about the three wires, the live wire and neutral wire, and also earth wire. The live and neutral wire have a potential difference of 220 volts, and the household circuits are connected in parallel because to offer low resistance. And then the use of earth wire, right? Any such or the additional current that will be absorbed back into the that earth wire puts that back into the earth, right? And then how this electricity bill is generated. That's based on the reading in the electricity meter, and that electricity meter is the amount of energy, electrical energy that is consumed, that can be calculated using V into I into T. We know the voltage 220 volts. We know how much current, if it is 5 amps into 5 into how much time it has been used. So if it is used for 8 hours, then 8 into 16 to 60, right? So then we will get the amount of current that we have used. If we convert that into kilowatt hours, then each unit you will get a charge, some amount. And if you multiply with the number of units you have consumed, you will get into the electricity bill. Okay. So that's all for today's session. I hope you all understood the topic, and I'll see you next time. If you have any doubts, you can reach me using my Urban Pro profile. Thank you.